Hi, welcome back to our astrophysics lesson series. If you're new here, please consider checking out our previous videos about Newtonian gravity, general relativity, and dark matter that will be helpful as we tackle our topic for today. So far in this series, we've covered about 32% of the universe, including baryonic matter and dark matter. Today, we're tackling the other 68%, dark energy. First, we need to lay some ground level information. The universe is expanding. This diagram can be helpful in understanding the expansion of the universe. It is important to understand that the vertical axis on this diagram represents time. So the very bottom of the diagram is the birth of the universe, and as you move up the diagram, each level represents a younger and younger universe until the very top level, which represents present day. The top of the diagram shows us what is happening in the universe now.
It's expanding, and it's doing so at an accelerating rate. This means that the universe is expanding faster now than it was 20 years ago.
The very bottom of this diagram represents the birth of the universe at the Big Bang.
At the Big Bang, the universe was born in a tiny point of mass and energy. And initially, it expanded very quickly. We call this period of time inflation. And the interesting thing about inflation is that the universe seemed to expand proportionally. All this means is that it stayed about the same, just got bigger. So if you had a picture and you wanted to make it bigger but have it still look the same, you would need to expand it proportionally. This is in essence what happened to our universe. The reason it did this is the mass energy density of the universe. So the amount of mass and energy per cubic meter of the universe was the perfect amount to make the universe expand proportionally. If we had had a higher mass energy density, there would have been more gravity that would have been able to overcome the force of expansion. This would have resulted in a sort of globe-like shape of the universe. But if we didn't have enough mass energy density, then the gravity wouldn't be enough and the force of expansion would cause the universe to be shaped more like a rainbow or a hyperbolic shape. But neither of these scenarios happened. Our universe had the magic amount of mass energy density, allowing it to expand proportionally. So that means that our universe is what we call flat. This just means that the spacetime continuum is a perfect grid. It doesn't curve on its own without other masses there. So if we released a small mass out into space without any other large masses nearby, it would just travel in a straight line. Now, how do we actually know that this is the case? Well, we can measure the cosmic microwave background of the universe. In our dark matter video, we touched on what the CMB is, but as a refresher, the Big Bang let off massive waves of heat and energy, and they're still ricocheting around our universe today. We can measure them, and they don't curve like they would if our universe was shaped like a globe or in some sort of hyperbolic shape. This tells us that our universe really is flat. So a flat universe with gravity, like ours, will expand more and more slowly until eventually it stops.
But physicists were measuring light emitted from supernovae, and they were more dim than they should have been according to this model. The supernovae should have been moving away from us, but at a slowing rate. However, that's not what was observed. These supernovae were moving away from us at an increasing rate. That's when it was discovered that not only is the universe expanding, it's doing so at an accelerating rate.
Scientists also realized that there is no center to the expansion.
It's like the universe is clay. There's some sort of mysterious rolling pin that expands the size of the universe. Every spot in the clay is expanding at the same speed. Even though all their speeds are the same from an outside frame of reference, from one point in the clay, some other points may appear to move faster than others.
To an earthbound observer, the apparent motion of a galaxy all the way across the universe is much faster than the apparent motion of Mars. So it's really hard to measure the expansion of the universe between the Earth and Mars because they're so close together. That's why we usually measure the expansion of the universe between the Earth and a galaxy far, far away. Based on these observations, the speed of the expansion of the universe has been measured to be about 68 kilometers per second per megaparsec.
A megaparsec is a distance, specifically 3,260,000,000,000 light years.
That number is not really important unless you're going to try to do math. So what's important is that you understand that a megaparsec is a really, really, really large distance.
So this speed says that if we look at a galaxy 1 megaparsec away, it will appear to be receding from us at 68 kilometers per second. If we take a galaxy 2 megaparsecs away, it will appear to be receding from us at double that, 136 kilometers per second. And this pattern continues as we get further and further away.
That may make it seem like Earth is the center of the expansion, but we see this same pattern when measured from other points in the universe. That's all fine and dandy, but how fast does that mean these galaxies are actually moving? Well, if you work through the math for one galaxy at a time, you'll find that this exceeds the speed of light. How is that possible? Special relativity dictates that nothing can move faster than the speed of light. Well, special relativity is a local law, so it only applies to situations in which the observer is close to the thing moving the speed of light. For example, you will never see a rocket ship blast off Earth at the speed of light. But a galaxy all the way across the universe from us? Special relativity doesn't apply, and its apparent motion may very well be faster than the speed of light.
We don't know why this expansion happens, but we call the phenomena that's causing it dark energy. Dark energy seems to be a force in opposition to gravity. Gravity causes masses to be attracted to one another, whereas dark energy seems to make them spread out. There are two theories for what this dark energy is made of.
Theory 1 is that dark energy is just a property of empty space. It has no mass and resides in the space between galaxies. This theory speculates that the expansion acceleration can be represented by a single number called the cosmological constant. Just like we can say that your car's acceleration is 12 miles per hour per second, we can say that the expansion acceleration is a certain number.
Lambda is the variable we use to represent this number, the cosmological constant. This constant is used in Einstein's general relativity equation to correctly model the forces acting on spacetime.
General relativity is Einstein's explanation of the bending of spacetime that causes gravity. We put the cosmological constant, or lambda, in this equation to balance out gravity and create accurate predictions for the movement of objects within the spacetime continuum. For a more complete explanation of general relativity and the history of the cosmological constant, please see the video that I made about that on my channel. Theory 2 is called quintessence. Quintessence would be some sort of field that extends throughout all of space and causes the acceleration of the expansion of the universe.
The word quintessence comes from the Middle Age when people named a fifth fundamental element. So there was earth, fire, water, air, and quintessence. We use this word for a dark energy theory because dark energy would be a fifth fundamental force of the universe. The other fundamental interactions are strong force, weak force, gravity, and the electromagnetic force.
The quintessence theory is a bit more involved than the lambda theory. It says that the expansion of the universe relies on more than just the amount of empty space in the universe. So it relies on the pressure of empty space and the energy density of empty space. Except empty space isn't actually empty. It has lots of energy and potentially lots of very small particles. So the pressure of this space is kind of the same idea as air pressure, except with all of this energy and mass that fills the space between larger masses. Energy density is a measure of how close together or how spread out the energy in the universe is. So if there's an area of high energy density, that would be an area that has lots of energy close together.
The equation for this theory of expansion is W equals P over rho. P stands for pressure and rho stands for energy density. We use W as a metric for determining the rate of expansion without producing an acceleration. The more negative W is, the faster the universe expands. Basically, scientists needed a way to compare the two theories, so they created this scale where W falls somewhere between 0 and -1. If W is closer to -1, the universe is expanding faster than if the value falls closer to 0.
The cosmological constant theory has a W value of -1. The quintessence theory, on the other hand, allows the W value to change at different points in space at different times. So this means that the quintessence theory better explains how the universe had different rates of acceleration at different points in its past. This also means that different points in space can have different amounts of acceleration. It's a scalar field. So this tweaks our sugar cookie analogy just a little bit. Instead of dark energy being like some sort of mysterious rolling pin, dark energy is more like a game of whack-a-mole. This just means that our galaxy might be expanding faster than a galaxy somewhere across the universe.
Both of these theories are very possible, and scientists are doing lots of work on both of them. The truth of the expansion of our universe may lie in one of these theories, a combination of both, or something different altogether. So, what does dark energy mean for the fate of our universe? What happens when dark energy causes things to be majorly spread out? Well, most theories predict that the universe will end, and there are 5 big universe end theories that all stem from the theory of dark energy.
The most likely universe end theory is the Big Freeze.
This happens when everything gets so spread out and there's no more material for making stars, so everything gets really cold. The universe would approach absolute zero. Hence the name, the Big Freeze.
Another theory that is also likely is the Big Rip. This theory says that dark energy will not be strong enough to overcome the gravity that keeps galaxies together, and therefore separate galaxies will get ripped apart, and sections within those galaxies will also get ripped into their tiny particles. Hence the name, the Big Rip. The other 3 theories have less scientific support. One of them is the Big Crunch. This theory says that eventually gravity will prove stronger than dark energy, and everything will get crunched back down into a singularity, like at the center of a black hole or where the universe was born at the Big Bang. Then there's the Big Bounce. This theory is more of a combination of the Big Crunch and the Big Bang. So it says that the universe will get crunched down to a very small point, and then it will bounce back into a new universe. Another theory is the Big Slurp. This theory says that the universe is a false vacuum, meaning that there's space between big masses like the Earth and the Sun, but that space has lots of things in it. Now, this could become a true vacuum at any point, and if that happened, it would instantaneously annihilate all mass, or slurp us all up.
However the universe ends, or if it ends at all, we sure have a lot to figure out before then.
Huge thank you to David Whitaker for helping me with this script.
Dark energy is one of the most highly researched physics topics in the world today. In our next video in this series, we will be delving into another highly researched topic, black holes. I hope to see you then.